Welcome back everyone. In this example, we continue on looking at how to prepare a buffer solution. And specifically, we're looking at this question is specifically looking at an example where we're given a list of available acids in a laboratory. And we need to explain how we're going to prepare a buffer solution if that we want a pH of 7.99. So in other words, we want to prepare a buffer solution with a specific pH. And we have a list of acids and conjugate bases to our disposal, and we need to make some decisions. So let's start the analysis, right? So we want a pH, where's my pen? pH must equal to 7.99. So that means usually what we start by is we're looking for something with a pKa in the region of the pH. And looking at these numbers here, right, the only one with a pH close to it, doesn't have to be exact, but meaning the closest to 7.99 is the pKa of the pKa which is equal to 7.21. And that is of course that of the dihydrogen phosphate. So in other words, we choose dihydrogen phosphate. All right. Now, your question might be immediately, all right, so we choose dihydrogen phosphate, but is that then hence our acid or is it our base? And the answer lies in the fact that it has a pKa close to our pH. So meaning it is the acid. pKa meaning it's the acid. So if that is our acid, right, so meaning that is the acid, that means we need to choose, still need the conjugate base. So we need to combine that with a conjugate base, and its conjugate base is of course hydrogen phosphate. Right, so that's hydrogen phosphate, HPO4 2 minus. And that is going to be our choice of buffer. Right, so we already know the pKa is very close to the pH. And now the question is, how are we going to get that pH exactly to what we want? Well, the answer lies in we need to fine tune, let's call it fine tune our ratio of the base concentration to acid concentration. Right, because if you analyze the Henderson-Hasselbalch equation and look at what it says pH is equal to pKa plus log of the concentration of the conjugate base divided by the divided by the acid concentration. All right, and if we now put in what we have at the moment, the pH that we want is 7.99, and our pKa for our base of our acid is 7.121, and our choices of acid and base, the base is hydrogen phosphate, and the acid is dihydrogen phosphate. All right, so that means that if we solve this a bit, that 0.78 is equal to log concentration of HPO4 2 minus divided by H2PO4 minus. All right, so meaning that we essentially want to make up for that discrepancy of 0.78 0.78 by fine-tuning exactly what must the ratio of those two concentrations be. Right? That's what the Henderson-Hasselbalch equation implies to us. So let's continue on solving for the ratio. So that means our ratio of HPO4 2 minus divided by the concentration of H2PO4 minus must be equal to 10 to the power 0.78, which is equal to 6.025 and so forth. And we can round that to a ratio of about 6. So for example, so meaning our base needs to be 6 times whatever our acid concentration is. That's what we've gotten here. So whenever our base is 6 times whatever the acid is, our pH will be 0.78 units higher than our pKa value. And that actually makes kind of sense, because if the base is a bit more in excess, in other words 6 times excess than the acid, our pKa should rise with a couple of units, and exactly 0.78 units. So that's just basically what we've determined here. So for example, if we choose that we take 0.6 molar HPO4 2 minus, and we take 0.1 molar H2PO4 minus, then we get a ratio of 6.0. Right, and you see the base has 6 times the concentration of the acid. And because they're in the same volume, this means this is actually also the mole ratio. So that means if we take 0.6 mole of HPO4 2 minus and 0.1 mole of H2PO4 minus, we also need to have a ratio of 6. Right? This is because of same volume, meaning they're in the same buffer solution. That's why they have the same volume. So to make up our solution, what do we need to do? So let's say, therefore, we need to choose. What do we need to do? So we choose, say, 2 salts. So the one salt needs to be HPO4, NaHPO4, and the other salt, let's also choose a sodium salt. It can be any salt really, so it just has to be a salt. Right, so the one gives us the conjugate base, the other one gives us the acid, and mix in 1.00 liter in a molar ratio of 6 to 1. Alright, and that's how we will get a pH of 7.99, is we do that. Alright, they didn't ask for exact masses, but in principle you can calculate exact masses, because we know we need 0.6 mole of this and 0.1 mole of that, so that means you need 0.6 mole of something like this and 0.1 mole or something like that. So you can go and calculate the masses if the question, for example, specified that. It didn't specify that, so we can leave it in the sense that you just need a molar ratio of 6 to 1. If the question said what masses, but we don't have to go into too much detail. I'm quite certain from the number of moles you are capable of calculating the masses of the species. All right. So that's how you can prepare a specific pH from known pKa values. So the pKa is roughly equal to the pH that you want, and then that's your ballpark estimate, and then you use your concentrations to fine-tune your pH of your buffer solution. All right, good. Thank you for watching, and I'll see you in the next video.